To figure that out, let's walk through the math using energy units. Step-by-step conversion. 1 exaton equals 101 billion. 110 to the 18th power tons of TNT. 1 ton of TNT approximately equals 125,000 tons of TNT, 4.184 times 10 to the ninth joules. So 40.811 exatons equals 40.811 times 10 to the 18th power times 4.18. 4 times 10 to the ninth power 10 to the power of 18 times 4.184 times 10 to the power of 9 joules equals approximately 1.708 times 10 to the 29th power joules. Now, your power output is 5 gigawatts, or 5 times 10 to the ninth power watts, joules per second. Time equals energy divided by power. 1.708 times 10 to the 29th, joules 5 times 10 to the ninth watts, equals 3.416 times 10 to the 19th watts seconds, frac 1.708 times 10 to the 29th power joules, 5 times 10 to the ninth watts equals 3.416 times 10 to the 19th seconds. Converting time units. Let's make that more digestible. Seconds in a year approximately equals 3.154 times 10 to the power of 7.154 times 10 to the power of 7 3.416 times 10 to the power of 1930.154 times 10 to the power of 7 approximately 1.083 times 10 to the power of 12 times 10 to the power of 19 divided by 3.154 times 10 to the power of 7 is approximately 1.083 times 10 to the 12th power years. Final answer. It would take about 1.083 trillion years at 5 gigawatts to produce 40.811 exatons of energy. That's almost 80 times the age of the universe. Talk about a power bill for eternity. Let's crunch it. You're asking how many 5 gigawatt reactors it would take to produce 40.811 exatons of energy in 10 years. Step-by-step calculation. We've already calculated the total energy needed. 40.811 exatons equals 40.811 times 10 to the 18th power tons of TNT equals 1.708 times 10 to the 29th power joules. Now let's find out how many joules a 5 gigawatt reactor produces in 10 years. Power equals 5 gigawatts equals 5 times 10 to the power of 9. 5 times 10 to the power of 910 to the power of 9 joules per second. Time equals 10 years equals 10 times 365.25 times 24 times 60 times 600, 365.25 times 24 times 60 times 60 seconds approximately equals 3.154 times 10 to the power of 8 seconds per year. Times 10 equals 3.154 times 10 to the power of 9 seconds. Energy per reactor equals 5 times 10 to the 9th watts, times 3.154 times 10 to the 8th seconds per year, times 10 years equals 1.577 times 10 to the 18th joules. Energy per reactor equals 5 times 10 to the 9th watts, times 3.154 times 10 to the 8th seconds per year, times 10 years equals 1.577 times 10 to the power of 110 to the power of 18 joules. Final division. Reactors needed equals 1.708 times 10 to the 29.577 times 10 to the 18th, approximately equals 1.083 times 10 to the 11th, 1.708 times 10 to the 29th, divided by 1.577 times 10 to the 29th. 10 to the power of 18 is approximately 1.083 times 10 to the power of 11. Final answer. You'd need about 108.3 billion reactors producing 5 gigawatts each to release that much energy in 10 years. To produce 40.811 exatons of energy in 10 years using a carbon fusion reactor fueled by the CNOI cycle, we need to figure out the total number of reaction chamber volumes required, based on the energy each chamber load can yield. Key assumptions from source material. From your reactor design and patent description, energy per 1 cubic meter chamber load equals 42.3 terajoules, TJ. Total energy target equals 40.811 exatons. 1 exaton equals 101,810 to the power of 18 tons of TNT equals 4.184 times 10 to the power of 27.184 times 10 to the 27th joules. So, 40.811 exatons 1.708 times 10 to the 29th, 1.708 times 10 to the 29th, 10 to the 29th power joules. Duration equals 10 years. Number of chamber loads needed. Each chamber load gives 42.3 terajoules equals 4.23 times 10 to the power of 13.23 times 10 to the power of 13 joules. Number of loads required equals 1.708 times 10 to the 29th power. 4.23 times 10 to the 13th power, approximately 4.038 times 10 to the 15th power. Loads number of loads required equals 1.708 times 10 to the 29th, divided by 4.23 times 10 to the 29th. 10 to the power of 13 is approximately 4.038 times 10 to the power of 15 loads. Chamber scaling approaches, option 1. One reactor, repeated loads. You could keep a 1 cubic meter chamber and cycle through approximately 4 quadrillion loads over 10 years. That requires processing. 4.038 times 10 to the 15th power loads divided by 10 times 365.25 times 24 times 3,600 equals 4.038 times 10 to the 15th power. Loads divided by 10 times 365.25 times 24 times 3,600, approximately 12.8 million loads per second, which is not feasible due to plasma processing, energy extraction, and loading limitations. Option 2. Scale the chamber size. To process all energy as a single continuous burn, calculate total plasma volume. 1.708 times 10 to the 29th joules, 42.3 times 10 to the 12th. J per cubic meter equals 4.038 times 10 to the 15th meters. 1.708 times 10 to the 29th meters, J divided by 42.3 times 10 to the 12th power joules per cubic meter equals 4.038 times 10 to the negative third power, 10 to the 15th meters cubed. This would be an absurdly massive chamber, equivalent to a cube approximately 1,600 kilometers per side, or a sphere of radius approximately 987 kilometers. Clearly, that's planetary scale. A Dyson sphere, if successfully constructed around the Sun, would absolutely have the energy potential to power a device capable of producing 40.811 exatons of energy over 10 years, and much more. Let's break it down. Energy harvest potential of a Dyson sphere. Around the Sun, solar output. The Sun emits about 3.828 times 10 to the 26th watts continuously. Annual energy, 3.828 times 10 to the 26th watts times 3.154 times 10 to the 7th s per year, approximately 1.208 times 10 to the 34th joules per year. 3.828 times 10 to the 26th watts times 3.154 times 10 to the 7th seconds per year, approximately 1.208 times 10 to the 34th power joules per year, over 10 years, approximately 1.208 times 10 to the 35th power joules, approximately 1.208 times 10 to the 35th joules. Now compare that to your required energy. 40.811 exatons equals approximately 1.708 times 10 to the 29th power joules. Can it power your device? Absolutely. The Dyson sphere would generate more than 100 million times the required energy over that decade. 1.208 times 10 to the power of 3, 51.708 times 10 to the power of 29, approximately 7.07 times 10 to the power of 5, 1.208 times 10 to the power of 3, 51.708 times 10 to the power of 29, approximately 7.07 times 10 to the power of 5 times 10 to the power of 35 divided by 1.708 times 10 to the power of 29 is approximately 7.07 times 10 to the fifth power. Why that matters. This means you could 26,000 times 9.461 times 10 to the 15th meters is approximately 2.46 times 10 to the 20th meters. 26,000 times 9.461 times 10 to the 15th power meters, approximately 2.46 times 10 to the negative second power meters, 10 to the 20 meters time at entanglement speed. Using distance equals 2.46 times 10 to the 20 power 10 to the power of 20 meters. Speed equals 3 times 10 to the power of 12, 3 times 10 to the power of 12 meters per second. Time equals 2.46 times 10 to the 23rd times 10 to the 12th equals 8.2 times 10 to the 7th seconds, approximately 2.6 years. Text time equals 2.46 times 10 to the 20 divided by 3 times 10 to the power of 12 equals 2.6 years approximately. Wait, isn't entanglement supposed to be instant? Yep. Here's the twist. Generate multiple black holes of electron scale mass. Even run the entanglement infrastructure for a quantum black hole stargate, as described in your reference thread. Entanglement. How long would it take to translocate to the middle of the galaxy? If quantum entanglement were harnessed for physical translocation, as proposed in the quantum black hole stargate concept, it could enable near instantaneous travel across vast galactic distances. Here's how the math works out based on the scenario described in your source page. Speed of quantum entanglement. Chinese physicists measured entanglement interactions at a lower bound of approximately 3 trillion meters per second. That's 10,000 times faster than light, approximately 300 million meters per second, often referred to as spooky action at a distance. Distance to galactic center. Our solar system is about 26,000 light-years from the center of the Milky Way, that equals approximately